So, bonjour everybody. Welcome to the 5th Geopolymer Camp. It's now a tradition that I present at the beginning of the camp what we call the state of geopolymer research and development for the year 2013. That is what we consider as of having been very important during 2012 and 2013 in terms of news and development on the geopolymer field. The previous state of geopolymer are recorded, available on the web at the Geopolymer Camp page. 2009, it was titled Mass-Produced Geopolymer Cement. 2010, State of the Geopolymer R&D 2010, and so forth, 2011, 2012. The state of geopolymer research usually comprises 4 parts. First, geopolymer science. Second, geopolymer technology. Third, geopolymer cements and concrete. And fourth, geopolymer and archaeology. For those who are new, you know that we are strongly involved in adapting and in transferring our knowledge on geopolymer science to explain archaeology. Let us start with geopolymer science. I always repeat at the beginning the same and show the same picture. This was our first geopolymer conference in 1988, that 25 years ago at the University of Technology in Compiègne. So as you see, there were a couple of laboratories involved in it. It was a remote research, and this is what we have in 2012. Of course, the increase of laboratories and others working on the subject have a strong input on the numbers of publications published each year. I've stopped to count the publications in 2011. Now it's no longer necessary to show, to continue to look at the graph. We introduced this year a new way of communication with webinar. I guess it was for us. It was an experience. It was the first time that I made this type of communication worldwide. This has been the number of participants. We had 2 sessions, 2 days, Tuesday and Wednesday, morning session for the east part of the world, and the afternoon session for the west part of the world. We had 200 registrations and 110, 120 participants, which is for webinar on the web a very good participant number. 60% is something that is usually that is not usual. If we look at the map, so you see we had people from remote, from here, Murmansk, from here, on the Russia, Murmansk, close to the polar circle, and here from Mongolia, a couple of Academy of Science of Mongolia, they were attending and so forth. But I wanted to show you something that I do not understand. This is the map for Europe, and you see the number of people who had attended the webinar, but there are holes. I don't understand why we had nobody from Spain. Do Spanish don't have any access to internet? You know,
we have some people from the Spanish conference.
Well, well, please don't. Spaniards, scientists are all speaking English. It's not a matter of language. You know that we have the Geopolymer Chemistry and Application book. We had a small change. We changed the video, the CD, DVD for the tutorial into a new item. That is the USB stick that contains more videos in it, and it is adapted to the new equipment that we'll all have in 5 years from now. No more drives, nothing. Everything should be small and light in the equipment. So this is a new way of communication. In my book, I have at the end of each chapter the research which should be undertaken on topics in order to increase our knowledge. And I presented the roadmap on geopolymer science at the last Congress in 2008 in Verona at the big International Congress on Ceramics. And I will briefly show you where we are now. We had at the beginning 14 research topics. We have now 15. First, polymeric character of geopolymers. This is dealing with geopolymer micelle, nanoparticulates, technology of salt gel. Second topic, the water glass that I call polysiloxonate from a scientific point of view, soluble silicate. There are works done on microsilicate-based, silica fume, rice hulls, and so forth. Metakaolin, that at the beginning is strongly the base. We have now a synthetic metakaolin, not for producing cement, but for very special applications. Calcium-based geopolymer, this is based on high blast furnace slag. We don't have any new development. Rock-based geopolymer, we introduced the ferrosilate with the iron substituting the aluminum. Silica-based geopolymer, no precise development. Fly ash-based geopolymer, I am strongly trying to convince people who are using what I call the wrong alkali-activated fly ash process that is user hostile to shift to the genuine fly ash-based geopolymer. We will discuss it later. We have phosphate-based geopolymer that are the isomorph of aluminum phosphate. Organic mineral geopolymer, this is where in fact a lot of numerous various laboratories are working. First introduction of phenolic, water-based latex, ethyl ester silicate, and then we have silan and epoxy resins, and we will have more this morning. On long-term stability, durability, no improvement. On geopolymer fiber composites, there have been improvement for high temperature applications, and now the use of natural vegetable flax fibers. Geopolymer in ceramic processing, yes, high temperature ceramics by the introductions of, instead of sodium and potassium, cesium, lithium, gallium, and germanium. Manufacture of geopolymer cement, a new raw material. This is the ferrosilate-based cement. Geopolymer concrete, there is no improvement. In fact, the research are continuing. 15, material for medicinal application. This has been introduced 2 years ago. What I discovered this year was that there have been several studies dealing with adhesion, using geopolymer resin as an adhesives for various applications. And this is here a paper published in the Journal of Adhesion by a team from Brazil, Rio de Janeiro, Brazil, and it says, the abstract, adhesion properties of MK750 geopolymer-based adhesives on metallic substrate, steel and aluminum. These are the substrates that they studied according to different conditions: mechanical treatment, grid blasting, sandblasting, or chemical treatment, nitrophosphoric acid and silanizations. And the result is the effect of the individual surface roughness parameter alone is not statistically significant when correlated with bond strength. So it's not the surface, mechanical surface, that is important for our point of view. We know that having made several tests on adhesion on metal, what is important is the absence of any grease, oil on the surface. The geopolymer adhesive developed twice the strength in steel when compared with aluminum plates for any surface treatment type, reaching strength up to 5 MPa. So in fact, this is not a lot. What they achieved is medium. Because talking on working on steel, it is well known from the steel processing or manufacturing industry for coating that a metal like zinc plays a very important role in terms of adhesion. And we had a project that has been run for 3 years, and we applied on these special called zinc core steel, a very special geopolymer resin, very fine, 2.5 to 7 micron. No, this is the thickness of the zinc coating. We applied what we call the geopolymer Pipamel resin, 7 to 20 micron thickness. Very easy to polycondense, drying at 85 degrees C, polycondensation at 250 degrees C. And we achieve a corrosion strong, resistant material. The resin looks very complicated. It is a phosphate aluminum silicate based system that in comparison, these are the 7 microns sheet that we applied on our plates. So here you have the coating thickness for various industrial samples, very common material. This is regular galvanized, and here we applied our 7 micron geopolymer resin, and what we test is the appearance of the red rust, this is the bad rust on steel, in hours. So we achieve 1,500 hours, or here more than 2,000 hours, which represent for an automobile, I guess, if I remember, more than 50 years corrosion resistant for the metal. And adhesion is perfect, and this has been studied with Arcelor, and so far has not found regular applications for various reasons. Continuing with the adhesion on metal, the same group studied something very strange. Adhesion tests in quasi-crystals powders reinforced geopolymer composite. But this time they studied it to increase the adhesion on aluminum. The composite studied here consisted of a metacarline-based geopolymer matrix reinforced with quasi-crystal powders. The investigation were performed on quasi-crystal, aluminum, copper, iron, quasi-crystal, and the substrate consisted of anodized aluminum. In this week, the adhesion of the composite was investigated on aluminum joints, and this is what they have. where the increase of quasi-crystal, they get an increase of the strength. So they started from 4.9 and achieved 5.9, which is an increase of 25% by adding these exotic minerals. I communicated with them, and I thought, well, by introducing an aluminum compound in the system, we know that aluminum is very dangerous. It reacts with the alkali and produces hydrogen, and it is a way of making foam. And they said, no, we don't have any bubbles, we don't have any foams, which means then that the aluminum in the quasi-crystal is trapped, is no longer a subject of any reaction. I was interested in this paper, first for the performance, but second for something totally different. Quasi-crystals are complex metal alloys with atypical structures discovered in 1982 by Daniel G. Shechtman. So I was attracted by this name because I knew that Shechtman got the Nobel Prize in Chemistry in 2011, and I put this note on my personal website. Why? Because the news titled, this was the revenge for the ridiculed scientist. In September 2006, I read what I put on my personal website. My article, Publish and Perish, the Disease of Scientific Research, highlighted how the 2005 Nobel Prize winners in medicine had been forbidden for years to publish the results of their research simply because they contradicted what was taught in the faculties worldwide and accepted by the majority of the scientific community at that time. What was it about? They discovered that to heal ulcers and stomach ulcer was caused by bacterium, whereas in all medicine faculties it was taught for 100 years long, 150 years long, that is resulted from stress. So it contradicted what every people knew. Stress causes ulcer, dangerous, and they showed that it was the result of bacterium, and they were forbidden for any publication for 10 years or more. So it is not the first time, and the recent 2011 Nobel Prize laureate in chemistry, Daniel Shechtman, experienced a situation ever more vexing when in 1982, 30 years ago, he made his discovery of quasi-crystals. The research institution that hosted him fired him because he threw discredit on the university with his false science. This was in the US. And the Reuters news agency, dated in October 2011, ridiculed crystal work wins Nobel. So, this is a problem in science today. Those individuals that are making breakthroughs have really a problem to publish and to provide the news to the mainstream community. There are so many publications, and this is Publish or Perish, that it covers with the noise what is really important. And of course, I have often quoted in my books the philosopher Schopenhauer, namely, the establishment of the truth passes through 3 stages. During the first, it is ridiculed. In the second, it is resisted. And in the third, it is considered as self-evident. Daniel Shechtman has crossed the 3 steps. He was the subject of fierce resistance from one of the greatest scientists of the 20th century, Linus Pauling, Nobel laureate in chemistry and Peace Nobel laureate. In 1985, he wrote, "Daniel Shechtman tells nonsense. There are no quasi-crystals, there are only quasi-scientists." So of course, I was interested by this fact, because you know that I've been called also a quasi-scientist for a long time. Because what I am proposing, what you are coming in order to learn, this is a science that has been furiously opposed at the beginning, because ether does not exist. This is nonsense. Davidovits is inventing a new terminology, Davidovits is inventing a new chemistry that does not exist, and this is what is happening. Shechtman made his discovery in 1982. I've done it practically 2 or 3 years earlier, so it takes the time to really be adopted, and it is more and more difficult in our time. Or you are part of well-renowned institutions like MIT or Stanford and so forth, which is not my case, which was not the case of the others. And so, please, when you read news that the mainstream is not accepting something from 1 or 2 or 3 guys that are really promoting something new and extraordinary, then look at the facts and don't listen to what the mainstream is propagating. And of course, this is shown with the explanation is crazy. Ridiculed, resisted, self-evident. Okay, now we come to the applications of geopolymer science in aerospace, which belongs to science because it provides new requirements. This is a study that is ongoing, suitability of geopolymer for space applications, and it is in fact dealing with the making of the telescopes. So optics for the telescopes, the space environment presents unique challenges, vacuum, radiation, large thermal swing, and so they have their program. What are the geopolymer advantages? And you see that we are still dealing with adhesives. Seems that adhesions problem is something that the industry has to look at. It is something that of concern because we said that practically we have no problem in terms of adhesion, but in fact this is a new perspective market, niche market that is strongly strongly researched, especially in the US. So what is important is the initial low initial coefficient thermal expansion. Because of the thermal swing, it is obvious that we must have a very low coefficient of expansion, and these are the regular normal adhesives that are used, exotic cyanide ester, Rilin and so forth. And the geopolymer one here that they tested, they have between 8 and 15, which is in the range of what they are requesting. So a new material to be used in space must go through a rigorous test regime, outgassing, of course, thermal cycling, chemical interaction, no shrinkage during curing, and it must also be designed for the telescope's structures, and space qualified adhesive with limited ultraviolet aging effect. So they claim from the Air Force Research Laboratory in the US that they are way ahead The tests are ongoing. The results will be presented, and the geopolymer will be sent to the International Space Station for testing. This is the Space Station Experimental MEES 7. So we are still, these are small quantities of material that are requested, but they provide properties that can be used for other applications. You know that geopolymer has been strongly involved in motor car racing for composite, carbon-based and silicon-based composites. For the first time, we have a paper written by racing cars manufacturer. So this is McLaren, and this is the paper that have been published recently, 2013, in the publication in Composite, titled "The Development of High Temperature Tensile Testing Ring for Composite Laminates." This is by Advanced Composite, University of Bristol, and McLaren Racing Limited McLaren Technology Centre in the UK. What they have: this study aimed to develop a high temperature tensile strength test capable of testing fiber reinforced composite up to 1000 degrees C. Typically, traditional engineering ceramic matrix composites, CMCs, these are those that are used for high temperature, would be envisioned for these applications. However, one material which has shown potential for application in high temperature structures is geopolymer polysilate SiC silicon carbide composite. Polysilates are ceramics derived from inorganic polymers and processed through a polymerization chemical activation, rather than the extreme temperature processing synonymous with traditional engineering ceramics. This gives them a number of advantages over typical CMC materials, such as low production times, environmentally friendliness, and low density. So this is what they studied. So it is the flexural strength with the temperature, but measured at the temperature. Usually you take a composite, put it in the oven at 800 degrees C, let it cooling, and then measured at room temperature back. Here they measure at 800 degrees C, really. It was not easy for them to, this was the purpose, because this is what they are really experiencing. The material that is manufactured by our sister company is usually heavily used in racing cars, Formula One. When you see the brakes, when they are carbon brakes, they are highly red, high temperatures, and all this is protected with the geopolymer equipment, geopolymer part. That is, they are functioning at these temperatures. And this is what we have. So this is tensile modulus, and this is the tensile strength. Of course, it is not the geopolymer resin that is important, it's also the fiber that must also withstand this temperature. Okay. We are still working with adhesion, but this time now we will include organic-based systems. Here, this is an organic mineral that is silan in the system as an additive, and this has been done by the team at Urbana-Champaign, Illinois University, and the Dow Chemical Company. This paper details the successful synthesis of organic functionalized geopolymer through the addition of functionalized 3-alkosilane directly into the geopolymer matrix during the curing process. The silane coupling agent PAMS which is meta-acryl oxy propyl tetramelsilane, were used as received and added dropwise by mass directly to the metakaolin immediately prior to the addition of sodium silicate solution to form a slurry and applied to the structure. And they used as a substrate high impact polystyrene sheet and polystyrene foam. So this has been geopolymer on polystyrene foam. The results are good, but for me what was important is something different. First, they are using the proper geopolymer chemist terminology. And second, they have a statement on organomineral geopolymer hybrids. First, the geopolymer chemist terminology, they are not using what you find in papers dealing with cement. That is, we have something that has a gel or something undefined. They are using, well, this is the oxide ratios, molar ratios, and what is important, the quantity of meta-acryloproxylpropylene added was 0.070 mole per mole of geopolymer. So you have the organic molecules and you have the geopolymer molecule. And each of them has a molecular weight. Do you understand that? Do you understand that this is the proper way of thinking? That we are dealing with chemical structures that are well defined, and you should go away from the general wording of we are mixing something and we get a gel. The gel is very defined, is made of macromolecules that have a molecular weight. So, small calculations. The molecular weight for the silane here is 248. The molecular weight of the geopolymer, this is an NRP polysilate type. Here I took the dehydrated form, has a molecular weight of 428. So we know that the 0.072 mole per mole of geopolymer means 0.01, 217, 4.1% by weight off. But this is a type of reasoning that is important. This is a way of using the terminology and understanding it and propagating it. For those who had the chance of reading the patents that we wrote 20 years ago, 30 years ago, they will discover that from the beginning we used this terminology, moles. And there is also a general statement on organomineral geopolymer hybrids. So they write, despite the potential value of this line of investigation, little or no study of how geopolymer interacts with organic materials in general and coupling agents in particular has been undertaken. This document concentrates on the adhesive properties with the rationale that covalent and other strong bonding of the sizing agent into the growing matrix is necessary to prevent phase separation of organic and mineral materials. Normally, an organic material is solvent-based and the geopolymer are not miscible. So something must be done in order to let them be miscible. Well, this is what they wrote. 1 or 2 months later, there has been a publication that provided the answer. The answer, novel hybrid organic geopolymer material by the group of Napoli. They are still, she is here. And Dr. Giuseppina Roviello will present her keynote after my talk, after the coffee break. So this is the answer to the question that was risen by my friend Waltraud Kriven at Illinois State University. how can we how can we increase our knowledge on how to mix these two antagonist chemistry. Well, this is the paper that was published at the same time as the first one. Novel hybrid organic-inorganic materials were prepared through an innovative synthetic approach based on a co-reticulation in mild condition of epoxy-based organic resin and an metakaolin-based geopolymer inorganic matrix. A high compatibility between the organic and inorganic phases, even at appreciable concentration of resin, was realized up to micrometric level. Then these new materials present significantly enhanced compressive strength and toughness. What is this new synthetic approach? Well, it is based on the incorporation of the resin to the geopolymeric matrix suspension when both polymerization reactions are not yet completed. Good compatibility between the organic and the aqueous inorganic phases is obtained thanks to the numerous hydroxyl tails formed during the epoxy ring opening reaction that make the organic phase temporarily hydrophilic, increasing the compatibility with the aqueous inorganic phase. I show you a sketch. This is the geopolymer chemistry. We have the first step, polycondensation, the second step, and you have OH groups all around, and then this is the final step. The epoxy group, this is the epoxy, will also produce the OH group that will interact with this one. But there's a precise time before it is too early and after it is too late. So now let us go to geopolymer technologies. But in fact, with geopolymer technology, we still remain with mixing organic with geopolymer, but it's here the totally different processing system. There's a Chinese group at Guangzhou University, hot pressing forming process of PVC geopolymer composite materials. They first prepare MK750 based geopolymer paste, and then they add the PVC powder, they stir, refined on double roller, so they used their double roller equipment. After being repeatedly rolled at 150 degrees C, 170 degrees C for 5 minutes, thin 1 millimeter thick sheets were formed. So they process in a dry system. Subsequently, the sheets were laminated, stacked in a steel die, really, and hot pressed at approximately 170 degrees C and 10 megapascal for 5 minutes on the plate vulcanization machine. So they use the thermoplasticity of PVC in order to take the geopolymer in it. It was processed at 140, 170 degrees C, which means the water has escaped. This is what they get: flexural strength, geopolymer content, increase up to 40%, and then decreases, so there's compatibility up to 40%, and what they write is PVC price is higher than geopolymer material. Substituting some PVC resin with geopolymer, one gets higher temperature characteristic and lower fabrication cost. So you see the different approaches, those who are dealing with the chemistry in the liquid form and those who try to use their equipment. It is always equipment driven. Any development depends on the equipment one has been using. I will now show you something totally different, which is related to the proper use of the terminology, how it is important to use it properly. Essentially, if you want to get a patent. This is a patent that has been filed by people working on geopolymer material from a long time, Davidovits and so forth. And it is titled Process for Producing Geopolymers. What it is about, they take the ashes from the oil shale that has been burned for heating, for producing electricity, and they use it to make a geopolymer. The present invention relates to the production of geopolymers from oil shale and or mineral residues which originate from the production of oil by means of oil shale. To use the residues left in the combustion of oil shale, they are subsequently ground before they are mixed with an alkaline activator and water and cured. So depending on the mineralogy of the shale, they get reactive material and they apply it to manufacture what they say geopolymer cement-based system. Well, the patent was filed internationally, and they received the first answer from the patent office. You know, when you fly internationally, you get the examiner that is doing his proper international searching in order to find out if the patent deserves to continue, if it is a novelty, if it is patentable, and so forth. So this is the written opinion of the International Searching Authority on this patent, and they provide a list of 3 items: statement, reasoned statement on the rule with regard to novelty, invented step, and industrial application. Statement, novelty, no, except for claim 7, all others no novel. Invented step, no, invention. Well, maybe industrially applied, but they will not get any patent. Why? And the examiner provides the answer. This application does not meet the requirements of article so and so and so. What are the consequences? The term geopolymer used in the claims has no well-defined international accepted meaning in the prior art, as demonstrated by document D1 and D2. The term geopolymer lacks a uniform nomenclature. Moreover, D2 gives evidence that terminological and technical transitions exist between geopolymers sensu stricto, as defined by Davidovits, having 27 all LNMR spectra, having a peak and so forth, and obtained from the alkaline activation of metakaolin, and what are so-called alkali activated aluminosilicate binders. Hence, what is the geopolymer? When you open the literature, for a lot of people, something that is used to make a concrete. This is the geopolymer in general. At worst, for them, the geopolymer is alkali activated fly ash, period. And it is obvious that the examiner, the patent examiner that has to go through all the literature is getting these type of geopolymer used for cement and so forth that are based on alkali activated fly ash, and of course is also frustrated not to have a proper definition of what it is, because he knew that there are others that are using it properly. So learn the terminology. A geopolymer is not alkali activated compound, doesn't mean anything. It is not something that is coined AAMK, alkali activated metakaolin, doesn't mean anything. You cannot imagine the number of papers, scientific papers, that are written by people who are using all these acronyms. This is ridiculous. When I'm getting this type of papers for peer review, I reject them. Please use the wording alkali activated metakaolin, period, and not AAMK. And then or AAFA, alkali activated fly ash, or AAS. What is it? Alkali activated silicate. Wrong reaction that is deleterious to concrete, XXY, and so forth. We are dealing with geopolymerization in alkaline or acidic medium. So this is a concept. It is not a product, and you have to define it. If you want to get a patent, then you have to precise exactly what you get at the end, and use the proper terminology so that the examiner will really see where the invention is located and not in general terms. We have geopolymer binder and resin. So you see, it is not geopolymer, it is something. Binder, it is a resin. We are making paint, coating, grout. We have geopolymer cement. We have geopolymer concrete. Geopolymer carbon composite, and so forth and so forth and so forth. So if you have it first by the patent attorney, so I am doing geopolymer carbon composite, not just geopolymer, or I'm doing a geopolymer binder or geopolymer grout, so he knows where to look at. And we have several geopolymer molecular units. Remember, the molecules are important, and they are related with the constitution. These are the members, and these are the members. You'll find everything in the books, and you'll find everything on the web also. So I show you what happens when one applies the genuine geopolymer terminology. This is another patent, 2012, written by myself, for geopolymer cement or the ferrosilate type, abstract, binder or cement or the ferroaluminosilicate, FAO, SiO, geopolymer type, with some of the aluminum atoms substituted with Fa atoms, the whole satisfying the following raw formula. The geopolymer binder or cement is the result of a calcium geopolymer type geopolymerization with ferrometakaolin FAMK 750, and the written opinion of the International Searching Authority. Novelty, yes. Inventive step, yes. Industrial applicability, yes. That's the difference. So now we continue the exploration of what is happening in technologies, application of the geopolymer science and technologies. We have applications in the aeronautical field, and this is a European research and development project that is called KLA, I don't know why, which means the industrial implementation of new flat panels from renewable polymers and natural fiber reinforcement for the aeronautical industry. The aeronautical industry wants also to go green and use natural fibers to make panels for aircrafts. So this is the consortium, Belgium, Germany, Spain, and Spain here, and this is the European Research Center from Boeing. We have been working with the Research Center from Boeing since, I guess, year 2005. They started with one of our geopolymer resin that we shipped there, and this is where now they are. So they are proposing fire-resistant panels for aircraft interior involving flax fiber and geopolymer resin. They are doing the provision and technical requirements and specifications, development of panels based on geopolymers, evaluation of eco indicators. We arrive now to geopolymer cement and concrete. Something very unusual. From Australia, synthesis and characterization of mechanical properties in cotton fiber reinforced geopolymer composites. Composite is not the real term, it is cement and mortar. Fly ash-based geopolymer cement and room temperature hardening, this is what they are using. Alkali-resistant cotton fibers with an average length of 10 millimeters, average diameter of 0.2 millimeter, density 1.55 gram per cubic centimeter, tensile strength and so forth. And they see their results. Compressive strength with addition of 0%, they have 19, 0.5% by weight, 46, and then it goes down. Impact strength, same behavior with 0.5% cotton. Multiply by 2.5, the compressive strength. 0.5%. The problem is that if they add much, then the fibers start to co-agglomerate together and it's no longer working properly. But 0.5%, this is a very strong improvement. So I was surprised by this paper, and so it shows you that to increase the strength of the geopolymer cement, small minute quantity of additives may play a great role. We have studies dealing with the use of geopolymer cement for carbon dioxide resistant storage. This has been first developed by the company Schlumberger. They came to our lab 8 years ago, and they asked for, was it possible to use a geopolymer binder in order to pump supercritical CO2 gas in the empty oil wells and to plug it with the geopolymer cement, because supercritical fluid CO2 is a very aggressive acid, and it must be acid resistant, and it must go down to 2,500 meters sometimes, so there are technological requirements. And they promoted what they call the Evercrete system 2 years ago, I guess. So this has been the development from the product with several patents, and now we have the first scientific papers dealing with the same topic. So we have here a paper coming from Australia, permeability of geopolymer at downhole stress conditions, application for carbon dioxide sequestration wells, CO2 permeability of acid-resistant fly ash-based geopolymer cement under 3 axial conditions. So the CO2 permeability of geopolymer cement is between 2.10 minus 21 to 610 minus 20 square meters. That of CO2 used regularly for well is lower, from 10 minus 20 to 10 minus 11, which is practically divided by 10. This indicates that geopolymer is a good replacement for existing OPC-based cement, as it has lower CO2 permeability. Another application for geopolymer cement, this is the news that I put on our website. a company claiming to be the world's first production run 2,500 tons of geopolymer concrete. You see, it's not the making of geopolymer, it's the making of geopolymer concrete. I added this, it is metakaolin slag-based geopolymer cement that has been used by the company Rockla, and these are, they manufactured 3,000 of these grey crypts. These are parts, and they were working on geopolymer cement and geopolymer concrete application since the year 2005, first using it to produce sewage pipes, because sometimes for pipes what is required is acid resistance. And the technology was developed, and this is now what they are currently developing and manufacturing. This is something that I presented last year, but I want to come back to it because it relates to what is what I'm being presenting after. I received a mail that reads, "I would like to share the commercial success of our geopolymer technology for paving blocks and tiles from steel slag, fly ash and GBSF, ground blast furnace slag combination. The technology has been developed, transferred and commercial production started, has produced around 0.5 million bricks and got first purchase order of 3 million USD. Finally, we are planning to have 10 commercial installations in India in coming 5 years. Dr. Sanjay Kumar, Principal Scientist Resource, Energy and Environment, National Metallurgical Laboratory, it is Miamhetspur, India. Dr. Kumar came to Saint-Quentin in 2005. We had our World Congress. We discussed. He went back and they developed it commercially. It is a success. This is what they are doing. These are paving tiles from steel slag, and they claim it is a cement-free process. Uses eco-friendly geopolymerization process. I received another mail later, 1 year later, or 6 months later, development of cast in situ geopolymer concrete structure at CSIR, Ampri, Bhopal, India. Respectively, you are the father of geopolymer material, and we need your blessing in further R&D work in this field. Further, we are happy to inform you that our team has constructed cast in situ cement-free, advanced, reinforced green geopolymeric concrete with regards. So what they have done is a concrete structure. They are doing, you see the steel bars, and you see the concrete structure. This seems small, fine, room temperature, but it is something that represents reality. It is totally different from this one that is just a block of geopolymer fly ash based concrete, and that is on the web. This is what you get as a photo here. So it's easy to make a block. It is more complicated and more interesting to make a real structure, and this is what has been done in India. I put, you know that I put on the web the review Geopolymer Cement, review Geopolymer Cement 2013, where I describe what is for us the geopolymer cement. First, a clear cut between the confusion always made between geopolymer cement and geopolymer concrete. I repeat, a concrete is a material that consists of cement, geopolymer cement, and aggregate. So this is why it is important. We have geopolymer cement, and with the geopolymer cement you manufacture geopolymer concrete. And here, this is geopolymer cement. It is just the binder that we are describing. We are not describing the material that is the result of adding aggregates, of adding rebars and adding anything else. So, the problem is the following. You know that the existing Portland cement standards are not adapted to geopolymer cement. Geopolymer cement is better than Portland. The tests will do it. So if you have to test the acid resistance of geopolymer cement, there's no standards. What you take is the Portland cement standards that are nothing, that are too weak for us. They must be created by an ad hoc committee, yet to do so, and this is important, requires also the presence of standard geopolymer cement. So, this is what I'm propagating when I go somewhere, when meeting with civil engineers at universities, at the industries. It is important. When civil engineers are trying to make a new structure, they purchase a bag of Portland cement, and then they make their concrete, they make their structure. They don't manufacture in their lab the Portland cement. It is a standard material. This is what we must have for geopolymer application. Otherwise, the geopolymer concrete application will never start. Today, you have a lot of civil engineers who see that, oh, it is very easy to manufacture geopolymer cement. I take one mud, I take one fly ash, I put some alkali in it and stir, and I have something. And then they present their results. And the results are miserable. But they say, well, by applying the proper procedure, maybe we will achieve something that is better. So this is wrong. There must be standard. And the standard must be supplied by industry. That is, those who dare to take the burden of manufacturing this standard cement. This has been my talk last year, so please go back home and look at Geopolymer 12, State of the Art, and I'm strongly explaining why this is important. I've so often experienced the case that civil engineers were presenting results that were bad, and this was a bad publicity for what they were doing, just because they did not have the standard geopolymer cement or did not ask one of their colleagues that knew how to make it in their lab. So this is clear. Making a geopolymer cement must be done by people who have the skill and who learn and be specialized, experts in making geopolymer cement. And then they provide 1 kilogram, 2 kilograms, 20 kilograms to the civil engineer that will use it properly and compare then with and provide the data. Presently, every expert is providing his own recipe based on local raw materials, waste, byproduct or extracted. There is a need for selecting the right geopolymer cement category, so creating standards means selection. The 2012 State of the Geopolymer R&D suggested to select 2 categories, namely slag fly ash based geopolymer cement. Fly ashes are available in the major emerging countries. And then the ferrosilate based geopolymer cement, similar to rock based. This geological iron rich raw material is present in all countries throughout the globe. So we must select raw materials that will be available to make mass production. Of course, we start with niche applications. But the target is not to replace Portland, but to add to the Portland cement, because the the demand on cement to make concrete is increasing, is very here. Yesterday, Mr. S.K. Wally or Mr. Gupta stressed the fact that in India the demand is increasing and increasing and increasing, and not only in India, all over the world, except Europe and except the US. The standard fly ash and ferrosilate based, this is the chemistry, this is the kaolinite. 1 atom of aluminum is replaced by 1 atom of iron. We calcine and we get our ferromethakaolinate. So this is a new science that has been developed, it's 3 years young. This science has a major drawback. This technology has major drawback. Usually, in order to understand the geopolymer chemistry, we use nuclear magnetic resonance spectroscopy. But this is not possible because we have a too high amount of iron in it. So we must go to the Meusbar spectroscopy. That is to say, to learn about this investigation tool that is something very remote and exotic for everybody. So this is a red cement. It is no longer grey, it is red, like bricks, which is beautiful. And it is in development here in Europe, in Northern Ireland, by Bana UK, and Andrew McIntosh will present his small paper tomorrow. We have worldwide raw material for that type of geopolymer cement all over the world. This is characteristic of the geology. So if I look back to my webinar participation, I was struck by this fact. So look at India. Look at the number of scientists from India that were attending the seminar. This corresponds to what I knew from India, from the fact of the numbers of students, the number of people that are downloading our free papers from the library. I get practically 30% or 40% are from India. So there is a strong demand on the subject in India. And what is interesting is that I made a very short, very brief research on the subject, geological raw material for ferrosilate geopolymer in India. You have, for example, in Kerala state, it is southeast, but you have also all practically the 1/3 of India is from the geology so far, without not precise systems, has from the geology the raw material for the manufacture of this standard cement. And I know I can do it with Brazil, we can do it with South Africa, we can do it with all other major countries. So I'm now coming back to CO2 emissions. Comparison of CO2 emissions from Portland to geopolymer cement. This is also something that I presented at my webinar and also last year, but I will repeat it here. We had the news from Lafarge, that is the English translation. Lafarge implements a cement with a sharply reduced CO2 footprint. This new product, a clinker that is used in the manufacture of cement, one major constituent of concrete, has 30% less limestone, higher amounts of gypsum, clay or bauxite, that is silica-aluminates, are used, and Lafarge researchers claim achieving 25% reduction of CO2 emission. So this is, they filed for a patent that has been granted. It has been issued in 2010, and they are building the first pilot plant for that. The problem is the following with this information. We had at the Geopolymer Camp a French team that were presenting the comparison of CO2 emissions from Portland and Geopolymer. And they presented the following graph: concrete made with fly ash, blast furnace slag or metakaolin, and comparing with OPC in yellow and Geopolymer in blue. That is, we take the waste as they are. So first they compared metakaolin, and they found that it requires a lot of material, chemical ingredients that will produce a lot of CO2. Well, this is for scientists something interesting, but it is totally, it is ridiculous. From the beginning, we never used metakaolin as such as geopolymer cement. It requires too much alkali silicate. So this is the comparison that is made here just to denigrate the geopolymer system by comparing the fact that, look, MK-based geopolymer is emitting such a high CO2 content. If we compare with Portland, well, if you have here, you have on the scale 100 means 100% OPC concrete, 100%, and here they put for OPC 75. Well, I guess they are comparing OPC with OPC. The standard is 100, and they are telling that in fact OPC is 75. Why? Because they have been taking for granted the news by Lafarge that is claiming, wait, in 10 years from now, the OPC cement will only emit 75 in comparison with the hundreds of today. But they are, so this is what misinformation that is used in order to show that in fact OPC is as good as fly ash, 75, 45, well, emit twice CO2 than slag-based cement. So this has been in 2010. Then they published their results, and they wrote, well, what we have done was by taking the raw materials, fly ash and slag, as a waste, that is, not allocating any CO2 to it. But this is wrong in terms of calculation. From a scientific point of view, we must compare something totally different. Namely, we must take into account the CO2 emission if we would have manufactured the fly ash, manufactured the slag to make the geopolymer cement. And in that case, it appears that geopolymer concrete has a similar impact on global warming than standard concrete. So still comparing with metakaolin, obvious nonsense, but still having 75. Blast furnace slag and Portland equal, wrong, because 100% blast furnace slag is not a geopolymer cement. It is simply alkali activated slag, and this is not stable. Long-term durability, 0. So it is not a cement. It is not a geopolymer cement. Fly ash, if you manufacture your fly ash, it is obvious that you have to burn your coal in order to get the fly ash, that you emit CO2. So these are nonsense. The people who are using fly ash are using it because it is at their disposal. They are not so crazy that to manufacture the fly ash in order to make a Portland geopolymer cement. So this is the type of publication, scientific publication, that is taken as reference by the opposition, that say, look, This is the study, these are the results, and this demonstrates that Portland cement is a good guy. Okay? So when you see and look at papers that have been relating to this one, references, you know that this is misinformation. Disinformation. So this study highlights that future research and development now on geopolymer concrete should focus on two potential solutions. So they are not against geopolymer concrete, they know that there is a potential, but they want to develop it themselves. We must use industrial waste that is not recyclable within other industries. So don't look at fly ash, because we cement people want to use it for us. You have to look at other waste. On the production of geopolymer concrete, using a mix of blast furnace slag and alkali and activated clays, so make mixed, you must make composite, blending cement. It is only by adapting this direction that geopolymer concrete could allow us to achieve the current objectives for a long-term reduction of CO2 emissions. So they are teaching what should be done to make a genuine good geopolymer cement. And by doing this, they are reinventing the wheel. Because this is what we are doing. From the beginning, we have the geopolymer cement categories. Slag-based geopolymer cement was invented by myself in 1984 when I was in the US. That is 30 years ago. We don't need these guys to know what we have to do. Rock-based geopolymer cement, so we decrease the amount of slag, we decrease the amount of alkali needed, was invented in 1997. We had a European research project with 6 geological institutions to do this. Fly ash-based geopolymer cement is something that is, well, alkali-activated fly ash, forget about it. Slag fly ash-based geopolymer cement, and ferrosilate-based geopolymer cement 2010. So all these information are available. These people are aware of that. They are attending the geopolymer conferences. They are coming to the Geopolymer Camp and publish misinformation. If we compare the cement, the CO2 reduction between what we have and what Lafarge has, best case for Lafarge, 25% reduction, this is what they are claiming. Rock-based geopolymer cement, worst case, if we must manufacture everything, 70%. First, why? Because our temperatures are lower, because a lot of things, and of course I don't take into calculation the equipment that is totally different, that is cheaper, and in best case 80 to 90%. The problem is that there are other people who are doing the same. There's a paper 2013 from an Australian team at Monash University, carbon dioxide equivalent emission comparison between geopolymer and OPC cement. They are continuing what the others have done. The highlights: ordinary Portland cement has high embodied energy arising from a carbon footprint of geopolymers. An alternative binder to OPC was estimated. CO2 emission of geopolymer concrete is 9% less than OPC. Wow! Unlike past studies that shows 26 to 80%. So there's a new study that says everything is wrong. It's practically identical to Portland. Why? The key factors for high CO2 emission of geopolymers: energy expended on alkali activators, which means they are using a lot, and geopolymers need high temperature curing for strength, a further source of CO2, which means they are using the wrong alkali activated fly ash method, which consists of alkali activation. We dissolve the fly ash, zeolite formation. We use a lot of NaOH and N-silicate that are caustics. We cure at 80 degrees C, and this is user hostile. These guys never put their finger in the slurry. But this is what they are doing. 80% of the paper written on fly ash are made with this system. And this is what they are comparing. It is obvious that to produce this high amount of NaOH and silicate, you need a lot of energy and you emit a lot of CO2. But this is not what we are doing. First, we are dealing with a cement. A cement is a room temperature hardening system. If it requires temperature for hardening, it is no longer a cement. It is something else. They said, okay, it's fine for precasting, but it is not a cement. So forget it about the system. The fly ash geopolymer method, it is a room temperature hardening. Polycondensation, we react on the surface of the fly ash. We don't dissolve the fly ash. We just need a very small amount. We have 50 to 85% by weight of fly ash. We use a very, very weak potassium silicate solution. We use blast furnace slag as a chemical ingredient, activators, and water, and it is user friendly. And you see that we have practically a small amount of chemical ingredient that we have to purchase and to manufacture, and a high amount of fly ash, and it is user friendly, and it is a cement. So, if we compare with best case for Lafarge, fly ash based geopolymer cement, worst case if we have to manufacture all the ingredients except fly ash, because I don't want to be trapped by this tale that we have to manufacture fly ash, which is a nonsense. Best case, 90%. Last part, geopolymer and archaeology. We have our special session at 16:30 this afternoon. Just introduce some new items. So we have been studying Roman cement for a long, long time. For me, the genuine Roman cement is a prototype for geopolymer cement. And there is a paper, recent paper, that has been published very recently, 2013, that titled Materials and Elastic Properties of Aluminum Tobermorit in Ancient Roman Seawater Concrete. Cement scientists understand what it means. Tobermorit is the optimal molecule that represents the CSH. The CSH, when it polycondensed, could be tobermorit. It is a natural material, linear chain, SiO, 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 and calcium. So they studied very special pozzolanic material in the suburb of Puzzolane, Napoli, and they found that in the mortar they had what they call aluminum tobermorit. This is what we also found anyway. But the fact is the following. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cement scientists working on this. The difference likely arises from the presence of additional cations. The difference between CSH, regular Portland cement, or regular lime-based cement, Al3 plus and small amount of sodium and potassium. In the Bionusinus is the name of the true pozzolanes, in addition to thermal vibration. So one has aluminum, sodium, potassium in the system. The bonding environment of aluminum substitution for Si in the crystal lattice distributed by NMR study indicates long silicate chain length, so polymers, and pervasive tetrahedral cross linkage of the silicate interlayer with overall Q2Q3 2.59, which means geopolymer network.
Without naming it. Without naming it.
No, they don't name it. They don't want to. They don't want to shift from their terminology. It is long silicate chain length and low Ca-SiAl ratio 0.8 suggests a high degree of polymerization and Si4 plus binding energy, which typically produce strong cement paste. Forget about CSH, no longer there. This is geopolymer, high degree of polymerization. This is the characteristic of Roman cement. But to do this, you need the right geological raw material. So you'll see this afternoon also news about the pyramids. There's been an investigation involving paleomagnetism, which proves, this has been in Europhysics News, which proves that some of the pyramid stones are artificial. And this is what we are claiming. So this has been my state of the art of geopolymer science. Thank you very much.